Good morning everyone. In this video, we will present our group project with the title of Slope Remedial Technique in Slope Stability. We are from group 9 with 4 members, which are me, myself, Shapanini, Nur Aisha, Nur Maisara, and Nur Hana as the group leader. The slope failure on December 6 of 2008 at Bukit Antari Bangsa of Ampang, Selangor was taken as the case study. A little introduction to the topography of the place. It is hilly terrain that ranges in elevation from 133 to 203 meters above sea level. Tropical environment are the climate throughout the years is warm and humid. Annual rainfall likely will cause over water content in the soils that make it unstable and so slope failure happen, such as geological, geomorphological, and geomorphological structure will influence the weakening pattern rock. There are 5 categories of slope failure found by Cruden and Bernes, which are fall, or known as rock fall, topple, slide, or landslide, heterospray, and flow. The problem statement is slope failure at Bukit Antari Bangsa, Ampang, Selangor. The type of slope failure is landslide, where downward movement of the soil mass occurring on the surface of fracture due to rapid heavy downpour. In result case, the slope strength became unstable to govern and sustain the strength of the consequent house. The flowing water on the surface will cause corrosion. The higher the rate of erosion if the land in an area that is located on a height and steep as the slopes of the hill. An extremely heavy flow of water will erode the slopes, soil, and upper layer. In connection with the process, erosion landslide will occur on the slope of the hill, especially during heavy rain occurring. The purpose of this project is to categorize suitable technique for slope remedial work in geotechnical aspect, which will be answered in subtopic proposed technique of slope stability with its application and long-term stability.
Next, I will explain about the techniques of slope remedial work. What is slope remedial work? Methods include the modification in slope geometry, drainage, use of retaining structure, and internal slope reinforcement. First, geometrical method, where the stability of a slope can be strengthened by changing the geometry of a steep slope to a softer slope, either flattening the slope or backfilling at the top of the slope, where the angle is normally supported by corresponding together with soil. Drainage method is valuable in settings where surface and subsurface drain are properly maintained. Third, retaining structures are employed in this manner to withstand the pressing forces of the soil masses. Fourth, internal slope reinforcement, which the goal of rock slope stabilization with structural element is to assist the rock mass in supporting itself by putting in place exterior structures that are not part of the rock mass but support it externally. Retaining structure technique. Retaining walls is always the preferred method because of its versatility in a confined environment. There are 4 main types of retaining wall. First, gravity wall, in which the foundation of the wall provides the resistance from sliding and overturning. Second, cantilever walls, in which the support is provided from a vertical or inclined cantilever. Third, tight back wall, in which the vertical or inclined wall face is restrained by ground anchor to limit outward deflection. Last, reinforced soil walls, in which soil is reinforced by metal strips, plastic strips, grids, soil nets, or fabric reinforcement to allow the outer face to stand at relative steep slope and provide internal stability. Next, there are several factors that need to be considered before designing retaining wall. First, location. Understand the property border, stormwater management system, irrigation, and consider all geographical issues. Second, soil. The soil that sets the backbone must be evaluated to ensure that it is strong enough to sustain the wall. Third, design. The corresponding wall height, footprint size, slope, and setback angle based on the site elevation and grade to begin the design. Also, consider the natural movement of the trapped debris downslope due to gravity. Last is drainage. To ensure the wall has adequate drainage and that water does not accumulate behind it, by determining potential surface water sources and ensure that drainage near the wall location.
So let's continue for the long-term stability for the purpose technique. Hi, I'm Maisara. So let's continue my part. From slope failure at Bukit Antarabangsa, we have proposed using a retaining structure technique such as a retaining wall to reinforce the soil element and stabilize the slope. However, assessing the design life and risk of failure of the retaining wall is mandatory in order to forecast the probability of a threat. Loss of life, infrastructure damage, and utility service disruption are all the possible risks. So, at the certain limiting requirement for a long term, we need to consider such as the permitted stresses, strains, and also the displacement. The design life often indicate when a major upgrades costing about 50% or more of the structure's value are required. A structure's useful design life is largely influenced by its design, a construction, environmental condition, and maintenance of structure. So, other than that, we need to refer to the standard table, which is from the retaining wall design guide. So, it content about the design information shows as a typical maximum permissible static plus seismic wall movement, the typical minimum design life, and the design requirement. So, the recommendations are based on the height of the wall and its potential to compromise the structural integrity of nearby facilities of structure. A retaining wall design life by engineers and geoscientists British Columbia from 2019 incorporate both stability and a civil serviceability consideration. The design life is determined by the consequences of a failure for a stability reason. So next we go to the conclusion. So for a conclusion, what can we get from this study? So actually when we go to the retaining wall, it also can overcome the slope failure at Bukit Antarabangsa. So we have proposed to using the retaining wall, but we also need to consider about the long term for both for soil stability and also the structure design. It is important for a future engineer to choose the right soil stability and also consider the structure design. So last but not least, we need to do some research about the past research to become a reference for the future. And as you can see for the technique, we can see the past research about the slope failure. So that's all from us. Thank you.
Hi and Assalamualaikum. My name is Nurhana Fatimah Hanafia and I will present regarding the application of any standard. This part will present any standard reference for slope remedial technique. Then let's move on to the code of practice for earth retaining structures using British Standard Eurocode, which is BS 8002-1994. Syria Report 104 have been applied to a wide range of wall types and soil in the UK and overseas, including multi-prop embedded walls and even non-embedded walls. It has also formed the model for other documents providing design guidance such as the recently published BD 42 2021/00 Design of Embedded Retaining Walls. Since publication of Serial Report 104, several retaining wall design guidance, documents, and codes of practice relevant to embedded retaining walls have been issued, such as Code of Practice for Earth Retaining Structures, Geotechnical Design Part 1 General Rules, Design Manual for Roads and Bridges, Design of Embedded Retaining Walls and Bridge Abutments, British Steel, Piling Handbook 7th edition, the design and construction of sheet pile confer dams, temporary propping of deep excavation, which is guidance on design, the observation method in ground engineering, principle and application, and lastly, GeoGuide 1, Guide to Retaining Wall Design. Then, as for the design of specific earth retaining structures, using interrelation of Section 3 and 4 of BS 8002/1994, the first retaining wall is counterfort walls. The durability of the walls is A. Deterioration of structure, B. Protection against corrosion, C. Attack by ground or saline water, D. Detailing. For the A part, the structure should be designed for durability in accordance with Section 6 of BS 88110/1985. The permeability of the concrete should be low. The minimum cement content should be in accordance with Section 3 of BS 8110/1985. For the B part, the concrete cover should be in accordance with Table 3.4 of BS 8110/1985, where the concrete is liable to attack from constituents of the groundwater or where the wall is to be dam-proof. The back of the retaining wall and abutment should be painted with a suitable bituminous material or covered with self-adhesive plastic sealing or otherwise provided with a waterproofing membrane. As for the C part, which is attacked by ground or saline water, chemical analysis of any groundwater present should be made to assess its sulfate content so that a suitable concrete mix may be designed in accordance with Table 6.1 of BS 8110/1985 in order to achieve a high resistance. For the D part, which is detailing, attention should be given to detailing of appropriate drips at the top of the retaining wall, weep holes, and other points where water may accumulate, so that the unsightly blemish on the exposed concrete surface due to rainwater and waterborne detritus may be avoided. Second design of specific earth retaining structure is reinforced concrete walls. The materials for reinforced concrete work should be in accordance with BS 8110 Section 1, BS 5328 Section 1, and BS 5328 Section 2 or BS 5400 Section 4. As for the structural designs, where reinforced concrete walls rely on other structure for support, the construction sequence of the structures and the wall and possible changes in use which may affect the support should be taken into account in the design. Next, let's move on to the third retaining structure, which is gravity walls. In terms of bearing capacity design, the foundation should be in design for bearing capacity at the ultimate limit state with allowance for the inclination and eccentricity of the forces on the foundation in accordance with the standard procedure using NC, NQ, and NY bearing capacity factors. Lastly, in terms of the serviceability limit state, alternately, in soil which are at least firm or medium dense, experience may indicate that serviceability can be satisfactorily assured by the bearing capacity calculation. For undrained shear strength calculation, a modulus factor greater than 1.5 will be required in the range of 2 to 3. The pressure on the soil under the toe of the wall should be checked to ensure that it does not exceed the allowable bearing pressure. Reference should be made to BS 8004 Code of Practice for Foundation. That's all from me. Thank you.